Well, that's it. Hello and welcome to Slooh. I'm Paul Cox, your host for this special live Slooh Star Party. And together with our special expert guests, we're going to watch and learn about a colossal, and I mean gargantuan space rock that is making its closest approach to Earth this evening. It's the potentially hazardous asteroid 2011 UL21. But before we get into that, I want to share some news that broke just before we came on air. Slooh has launched a new grant to make space exploration accessible to 100,000 students in urban school districts. Now, this is an absolutely mega piece of news, and it means that school district leaders can apply for the grant before August 9th, 2024, to receive a free district site license, providing access to Slooh's online telescopes, our curriculum, and professional development for the 2024-25 school year. To learn more, hop over to www.slooh.com, check out the blog, and you will find the post that's on the screen now. Back to the live Star Party tonight. Now, over the course of the show, we are going to be watching live views of the potentially hazardous asteroid 2011 UL21 from our robotic telescopes in the Canary Islands, starting in around 10 minutes time when the telescopes spark up. Now, these are the same online robotic telescopes that students control every night here at Slooh while they learn about space and astronomy with our engaging quest learning activities. We'll learn about those a little bit later. And we've got a special quest all about this asteroid that we'll be telling you about in a few minutes' time. Now, the close approach of 2011 UL21, we should just call it UL21 for short, made a happy coincidence for us because it marks the beginning of the events to mark Asteroid Day and its related events here in Luxembourg, where we've been invited to attend. That's the reason for the strange backdrop. I'm actually in the hotel that we're staying in. Many thanks to Maud Morocchi and the Asteroid Day team for inviting us in such a beautiful city too. First time I've been to Luxembourg. Now, we have got a full day of lectures tomorrow where we're going to be meeting astronauts, space industry experts, those who are battling to safeguard the planet from these pesky space rocks, and those who see them as potential resources we can mine to further our exploration of the solar system and beyond. Then on Saturday, if you happen to be in Luxembourg, pop along and meet me at the Asteroid Day Festival, where I'll be at Slooh's booth to show dignitaries and visitors the delights of Slooh's online astronomy platform, helping to develop, hopefully, a new space workforce generation for the burgeoning space industries. We're going to talk about that a little bit later as well. Then Sunday is Asteroid Day itself, which is set on the anniversary of the famous Tunguska event, when an asteroid exploded in the atmosphere, destroying thousands of acres of woodland in Russia in 1908. We're going to learn about that and other actual impact events a little bit later during the show as well. Now, these objects, they do impact Earth. We've got Chelyabinsk more recently. That caused huge shockwaves and injuries when it burnt up in the atmosphere over Russia in 2013. But back to today's event, the close approach of Near-Earth Asteroid 2011 UL21. Now, those who have been here before to watch solar and lunar eclipses, asteroid close shave supernovas going boom, and all manner of other live celestial events over the last 20 years, will know that we'll have some fabulous live telescope views of the asteroid over the next hour. This is one that we did a few years ago. I think that one is a POFIS or maybe one of the others, but we'll look at that anyway. Now, don't forget that Slooh members can snap images from our telescope feeds to use in the Special Moments Quest learning activity, where members can learn about asteroids and create a stunning time-lapse animation using the images they've snapped. We're going to show you exactly how that's done at the end of the show. Now, don't forget, Slooh members can ask questions in the Star Party chat and Q&A. And I do know that some of our educators are in the house today, so lovely to see you and some of your students. And make sure you start snapping images on the Slooh members event page so you can create your asteroid time-lapse animation. Well, it's going to be an action-packed show, so let's dive straight in. Now, I mentioned expert guests, and I think it's about time we invited our first one on. I'm delighted to welcome Dr. John Bovair, Slooh's Director of Curriculum and author of many of the Quest learning activities that I'm talking about. Hello, John. Welcome to the Colossal Asteroid Star Party.
Hey there, Paul. I'm so glad to be here for this star party. It's going to be a lot of fun watching this rock fly away from Earth.
It is indeed. It is indeed. So, John, before we talk about the potentially hazardous asteroid, UL21, we need to give some advice to students and members who are watching who need to start taking some images for the special asteroid quest that you're going to tell us about.
Yes, definitely. So, when the telescopes start coming online, there's going to be missions that are on our Canary 1, Canary 2, and Canary 3 telescopes. So make sure that you have those open and start snapping images because you'll be able to use those images to make an animation, kind of like this one here, but in the one that you're going to make, the stars are going to be stationary and you're going to see the little asteroid whizzing by.
Exactly. Exactly. So, John, let's learn a little bit about this pesky space rock. I've been calling it 2011 UL21, but it has a longer official designation, doesn't it?
It does. It's asteroid 415029. Um, so what ends up happening is the UL21 is almost like a preliminary name, but as the minor planets discoveries are confirmed, the minor planet center assigns them with a permanent number, which is what the 145029 is.
And this isn't good for somebody who can't even remember their own mobile number, all right? So, who and when discovered this asteroid, John?
This asteroid was discovered by the Catalina Sky Survey, which is conducted at the Steward Observatory's Catalina Station, which is on Mount Lemmon, right outside of Tucson, Arizona. It was discovered on October 7th, 2011. Hence why it's
Hence that
2011.
part. Yeah, exactly.
Yes,
So,
actually, yeah,
um,
2011 is of course, the discovery year. U actually corresponds to the second half of October, and L27 means that it's the 713th asteroid discovered during that latter half of October 2011.
now, it made its close approach to Earth this evening, but how close did it come? We've got this diagram up on the screen.
Yeah, it came about that 6.5 million kilometers away, or about 4 million miles away. So, I mean, it was close, but it didn't get, too close to us, which is good.
I mean,
About
that sounds like quite a long way, but this is actually pretty close for an asteroid of this size. Just how big is it?
Yeah, this asteroid is pretty big. It's about 2.3 kilometers, which is about 1.4 miles in diameter. Although you may also see some reports that give a range about 1.6 to 3.9 kilometers. So it's definitely colossal.
I think we've got a nice little diagram of this, which is actually comparing it to a mountain in England, in Great Britain, but hopefully we can pull that up. So you just said there that it's got quite a large size estimate on it. Why don't we know exactly how big these asteroids are? Why do they have such wide size estimates?
It's a really good question. Without actually sending a spacecraft to the asteroid to see it in full, we really can only get clues about the asteroids based on what we can see of it. So, one of the primary methods of discovering or of measuring asteroids is actually by watching their brightness levels as they orbit. So asteroids, they're not perfectly spheres like planets are. They can be like potato shaped. And so these asteroids are actually rotating as they're orbiting. And as we can measure the brightness as these asteroids are moving, we can get clues about the shape of the asteroid, how big the asteroid is. And basically, the size estimate is one of the parameters in the models that they fit. And so, with any model, when you fit to data, there's going to be a little bit of range of variance. And this is what we got.
Some of the close approaches, I'm not sure whether this one is one of them. It is quite a large asteroid, but some of these close approaches are very, very useful for when these asteroids come into the range of our radio telescopes and radar basically, because then we can determine their size, can't we?
That's right. That's another primary method. By shooting out radio waves and waiting for the reflection of those radio waves on the asteroid to come back, you can then model the size and shapes of the asteroids. And so
Ah, there
by
it is.
combining different methods, you can actually get better measurements about what's going on.
So there's our size comparison. I think we're going to have a look at that slide a little bit later as well when we talk about the size of other near-Earth asteroids. But I've called this so far a potentially hazardous asteroid and a near-Earth asteroid. Can you explain to students watching what those technical terms mean? Maybe start with near-Earth asteroid.
Definitely. Near-Earth asteroids are a good place to start. So, yeah, near-Earth asteroids are asteroids that, on their closest approach to Earth, which is also called the perihelion, it's less than 1.3 AU. Now, in AU, 1 AU is the average distance between the Earth and the Sun. And so, to be near Earth, they have to be within 1.2 AU for its closest approach.
Now we're not going to go into too much detail. This little thing popped up on the screen before I was thinking it was going to come up. We won't go into too much detail on this, but these are 4 different types of near-Earth asteroids. Can you explain very briefly, John, the difference between those? And I would ask the studio, because the telescopes have now started up, so I would ask the studio to keep an eye on the live feeds so that we can take a look at those when they come up.
Definitely. So all 4 of these kinds of asteroids, these are all near-Earth asteroids. Their closest approach to the sun is less than 1.3 AU, but you can kind of see that the shapes of these orbits are all a little bit different. So these are the 4 categories of near-Earth objects that we have. The one that we're watching today is an Apollo type near-Earth asteroid.
Okay.
And you can learn more about these different kinds of asteroids in the special moments quest that
In
goes
the
along
special,
with the star party
exactly.
today.
So what makes a potentially hazardous asteroid? What makes this one a potentially hazardous asteroid?
So a potentially hazardous asteroid must be a near-Earth asteroid, so its closest approach is less than 1.3 AU, but it also needs to be larger than 1 kilometer in diameter in order for it to be considered potentially hazardous.
Okay, John, look, we've got the first live images coming in from the Canary Islands Observatory. That is based at the Institute of Astrophysics of the Canary Islands, our partners there. Now, what we're going to do here, John, is in the 2 main telescopes that we're going to be looking at tonight, Canary 1 and Canary 2. And some of these telescopes, by the way, if there are educators watching, some of these Slooh telescopes are large enough for your students to fit inside them. They are that big. But what we're looking for here, and this is what the Quest does, and we will explain this later in your second segment, but what viewers have got to keep an eye open for is what we're seeing there is a whole stack of fixed stars. We've scheduled the telescope, so it's going to carry on taking that particular spot of the sky. And the asteroid, UL21, is going to enter in from the bottom right, and it's going to come up, and at 40 minutes past the hour, it should be dead center in the image view. So we're going to watch it track across as a small white dot against background stars. Now, John, that's going to be pretty difficult to see, isn't it? To identify against other background stars. So how do astronomers go about identifying a tiny little object? In fact, look, we can see it already, John. Can you see it? I can see it.
Yeah, that's amazing. So in this case, the asteroid's moving so fast that instead of becoming a little point of light, it's a little streak coming across the
Yeah.
field of view. That is amazing.
Yeah. And we've also got
But
another streak in that as well. We've got those. So what we're looking at here, I don't know if the studio can just scroll down. That's it. Great. So this is where we want to keep watching. So just to the right, about a quarter of the way up the image, we can see 2 little white lines. That is the asteroid moving through the field of view during long exposures, because to capture faint objects like this, you need ultra cooled CCD cameras, which are research grade, and you have to take a long exposure. These exposures are taking 50 seconds each. But we've also, you can see another line, a diagonal line, cutting down across the corner. And we've actually caught an artificial satellite in that particular image as well. So what we're going to be doing is we are going to be capturing images. So everybody there who wants to do this quest, you can only do it by capturing the images this evening during the next half an hour to an hour. All right, so carry on snapping images from the live telescope feeds, and then you'll find them in the quest and be able to. John, you don't know what a relief this is to actually know that I scheduled the right coordinates for this particular asteroid so that we can see it and all of your work on the quest can be done. But anyway, what about other types of asteroids? There's a large body of them that kind of hang out in between Mars and Jupiter's orbits, aren't there?
There is. In the asteroid belt, there's a ton of asteroids that those are called the main belt asteroids. Then the three other most popular groups or populous groups are the trans-Neptunian asteroids, which are asteroids orbiting further away than Neptune, which include the Kuiper belt objects and the Oort cloud. And there's also Trojans, which are asteroids that share an orbit with the planet, but they don't actually collide with it.
Yeah.
And the fourth most populous group is, of course, the near-Earth asteroids.
So where do near-Earth asteroids come from?
So they're thought to originate in the main belt in the asteroid belt. So between Mars and Jupiter. So these asteroids are there, and due to various gravitational resonances from Jupiter and other large bodies in the solar system, it kind of kicks these asteroids out of their orbit and kind of sends them into the inner solar system. So hopefully we could see them, every one of those that happens, and figure out if they're potentially hazardous or not.
Exactly. And we're going to be talking about how students can both learn how to do that using Slooh's telescopes, but also forge careers doing that as well. Now, if we can go back to the live feeds, please, studio, we need to keep on those live feeds whenever we can. There it is. It's still down there. We're going to see the next mission will come up and it's going to edge further and further into this field of view. I'm so glad we've caught it. Now, thank you for now, John. You're going to be joining us later to show us how the Quest time-lapse animation tool works with some of the images that hopefully you're capturing now. I haven't got a window open, so I can't capture them at the moment. I'm so frustrated. But hopefully you're going to come back, show us some of the images that you've captured during the event, and to talk about some of the career opportunities that students can forge in the space industry and how using Slooh helps them develop the skills necessary for those exciting careers. Now, before you go, give students and members one last reminder of what they need to do during the rest of the star party to capture their images.
So if Studio can scroll up just a tiny little bit. So as you're watching these live feed, students, there's a camera icon button right there. So keep clicking that, and you're going to be capturing images from that telescope. And those are the images that you're going to be able to use later on in the quest to make these animations. And when I come back, like Paul mentioned, I'm going to show you actually how to put those images into the special moments quest and do the animation tool. So stay tuned.
Thank you, Dr. John Bovair, Slooh's Director of Curriculum. We'll see you soon. Now, let's have a quick recap. This is Slooh's live coverage of the Colossal, potentially hazardous asteroid 2011 UL21 as it makes its close approach to Earth this evening. Now, the event marks the start of Asteroid Day activities here in Luxembourg, where we've been invited. There's a public exhibition on Saturday, so if you're intending to go, please come and introduce yourself, where I'll be at the Slooh booth. Now, before we welcome Dr. John Bovair back to the show to show us how the special Quest learning activity works, we're going to learn more about near-Earth asteroids with longtime Slooh member Keith Wozaleski, who is also a school teacher. Welcome to the Star Party, Keith.
Thank you, Paul. It's a pleasure to be here.
Now, Keith, we've talked about what near-Earth asteroids are, but not how many of them there are out there hanging around in the inner solar system, potentially on a course for us. So how big are they and what are they made of as well?
Yeah, we have that slide. Let's, if we can fast forward to the eyes on asteroids, just to get a look at that asteroid belt again, where these objects are originating from. I challenge our viewers at home that they can start counting how many there are. The current estimate is there's anywhere from 1 to 1.2 million asteroids in this region that we call the asteroid belt.
Wow.
Half a million, 600,000 of them are large enough, and we know enough about them that they actually have numbers. So, this is what we're looking at. The cool thing about the asteroid belt is most illustrations show it in this way, these objects being very, very close together. The asteroid belt is actually not very dense at all. The distance between
Mm.
these objects are about 600,000 miles. So the idea that we see in popular films or in illustrations is that, it's impossible to fly through it. Not the
Yeah,
case.
not the
600,000
case at
miles.
all.
Yeah, that's twice the distance from the Earth to the moon. So these objects are not as close as they appear, but there's about a million of them.
And of course, the
And
numbers that you're talking about are these are the ones that we've discovered and know about. We don't know the full population yet, do we?
no, of course not. And I think this illustration shows that it's very difficult to calculate the total number that's out there. We know the large ones for the most part, but as Dr. John said, you have to be able to observe them first before you can calculate the size of them and to even see them at all. So that
Keith,
has a lot to do.
while we got the live image up,
Sure.
what do you make of this? It's quite satisfying, isn't it, to see this asteroid? We forecast exactly where it is with the help of Slooh members, actually, who have made observations of this and submitted them to the Minor Planet Center to help determine its orbit even better than it was already understood. But what do you make of it?
Yeah, that's a huge part of what asteroid research is about, finding out where exactly it is, because the orbits can be very difficult to predict. And
Mm.
Paul, as always, you do such great work in finding some of these difficult to find objects. Asteroids are tough ones. They're tough ones to capture and to know exactly where they are. And you
They
need to
are.
really use a tool like Dr. John has,
Yeah.
an animation tool. But we have
So
it here.
how big are they? Let's put to one side what they're made of, but how big are these asteroids? We know the number now, but how big are they?
Well, you can imagine having that many of them, they vary in size. So to be considered an asteroid, they have to be about 3 feet in diameter at least, larger than that.
Right.
And it goes anywhere from that size up to the size of a minor planet of, 500 to 1,000 miles, something like Ceres, the largest of the minor planets. Anything smaller than 3 feet, that's what we would consider a meteoroid. These are pieces of dust and rock out in space, not quite as large as an asteroid, but these are things that we'll see as a meteor shower, something like that.
I think we've got a cool diagram, haven't we, showing just a small collection of some of the sizes of
Yeah,
these.
we do. We have a size diagram here.
It's not that one. It's one of the others that shows a small
It's
population.
this one,
of
yeah.
them. There you go.
So when we look at this, and we look at the largest one in the image, that's approximately 132 kilometers across. That's
Okay.
huge.
Wow.
When we talk about what we're talking about today, UL21, something that's a mile or more, mile, 2 miles, we're looking at something the size of the smallest objects on that page. So, the size of these varies tremendously from very, very large, about a third the size of the moon, which we would call a minor planet, down to something that's, a couple feet in diameter. So this gives a pretty good indication of the range
Mm.
of the size of these. But the thing to remember is what we're seeing today, which is huge, a
Mm.
kilometer, 1 or 2 miles across, on this scale, compared to other asteroids, would render as, one of the dots. It's very, very small,
Yeah.
but can cause a lot of damage.
But exactly, most of the ones on that particular graphic would do some horrendous damage. But luckily, the larger asteroids like these, we know very, very precisely where they are and where they're going. Now, Keith, we've had some conversations in the past about Jupiter and its involvement in sending some of these rocks, our way. Does Jupiter help us by hoovering up some of these rocks, or does it hinder us by sending them hurtling towards Earth?
Yeah, it kind of does both. Jupiter certainly does attract bodies to itself. Jupiter has, the estimated 100 moons. We think of the four largest moons, but it also has a lot of captured asteroids in orbit around it. So it does do that. It does provide that service in protecting the Earth. However, it does also tend to kick out asteroids, some of which will go to the ends of the solar system, some of which will make their way towards us, just because of our orbit around the sun. So it kind of fulfills both functions. It is our good friend, but it does send things our way too. And that's where a lot of these main belt asteroids are coming from. They're coming out of the main belt, being kicked out by Jupiter, placed into an orbit around around the sun, and occasionally will pass the orbit of the Earth, and they become dangerous.
So Dr. John Bovair told us about near-Earth asteroids, but near-Earth asteroids as a category falls under a larger category of celestial objects that includes some of the most popular objects that students can capture with Slooh telescopes from time to time. So what's this larger category, and what else does it include, Keith?
Yeah, the larger category would be near-Earth objects, and the most popular object there, of course, is the comet. And we've been very lucky to see so many incredible comet missions. Every time, a comet comes into view and approaches the sun, so many amazing images from the Slooh telescopes with these comets that we see scheduled. Just wonderful, wonderful images. The difference here, of course, the asteroids are coming from the main belt. Comets live someplace else. They live out in that region beyond Neptune, out in the Kuiper belt. And we also have comets with longer orbital periods that will live out in the Oort cloud. So there is that category of object, the comets.
And we've got a potentially decent comet, possibly getting to naked eye, but I'm always hesitant to get involved in the hype on comets because so often they don't turn out as good as they may. But keep an eye open on the Slooh website because students are tracking a particular comet every night at the moment. Now, let's talk about the impact of asteroids. I talked about Tunguska and Chelyabinsk asteroid impacts during my intro. Can you tell us more about those two events, Keith?
Yeah, Tunguska, that's the reason we're here today. Asteroid Day celebrates this event, the visit of this asteroid on June 30th, 1908. A very, very not huge asteroid. It's about 160 to 200 feet. So it's technically beneath the size limit of what we consider to be hazardous, but it was very, very fast moving. It exploded above the surface of the Earth and had a wide-ranging impact. The shock wave was felt as far away as 100 miles. There was a magnitude 5 earthquake that was recorded in the region, leveled, as you can see in the image here, 80 million trees, and the path of devastation was about 800 square miles. And
it's amazing. I mean, they look like matchsticks, don't they? And, we're talking about such a huge, huge region. So how about Chelyabinsk, bringing us a little bit more up to date?
Sure. Chelyabinsk was, that's another Tunguska image here. The thing to remember about this is not considered size-wise to have been significant, despite this 800-mile radius of destruction. Chelyabinsk was an object that was discovered, it was observed, I should say, in 2013. This is a good one because it was very, very slow moving, had a very shallow trajectory in the Earth's surface, and it was recorded by dozens of dash cams. And we have a lot of video footage of this, which we don't normally get to see. It's very rare. There's only been, I think, 9 or so asteroids that have actually been observed. And this is one of them. The interesting thing about this is it broke apart. We don't have an impact crater for Chelyabinsk. It broke apart into pieces. And the threat here, or the damage here, was the shock waves blowing out glass, causing that type of damage. Yeah. And it was very, very dangerous because the instinct, of course, is to go out. And this thing wasn't just, glowing. There was also a long, smoky tail. You can imagine being in a large office building or something, saying, hey, you got to come here and check this out. Everyone goes to the windows, and then the thing explodes and the shockwave hits, and now you have glass everywhere. There are 100 people, I think, that were injured in this because of the shockwaves with the glass. It was dangerous.
There's another, I've been very fortunate to visit this, but there's a very famous example of an asteroid impact in Arizona, isn't there?
Yeah, this is the Barrington crater. So this is an aerial view. Looks exactly what we think of, I think, when we think of an asteroid, an impact crater, just like we see on the moon. This happened about 50,000 years ago. It's 160 feet wide, we think the asteroid was, and left a crater about a mile across. So again, this is direct impact. This is an asteroid that made it through the atmosphere, didn't burn up, didn't break up, just slammed into the Earth. And of course, we see this on the moon because the moon doesn't have an atmosphere like the Earth does, and left this huge impact crater in Arizona. It's a popular site.
If we could pop back to the previous slide, because I saw a wonderful internet meme the other day They showed a picture of this and said how lucky it was because the meteor just missed the visitor center.
Just missed the visitors. Isn't that
I
funny?
thought that was quite
Yeah, and the
amusing
thing
if
about
people get that. So
yeah,
tell us a
and
little
this was
bit.
a good example.
Yeah. Go on, Keith. Carry on.
No, I was going to say this is a good example of asteroids that are slow moving. You know,
Yeah.
they make it through the atmosphere. We talk about ram pressure and ram speed. You know, you imagine an object coming from outer space traveling at a very, very high rate of speed. When it hits that point where the atmosphere begins and space ends, that area about 50 to 60 miles above the surface of the Earth that we call the Kármán line, it's really more of a region. If an object is moving very, very quickly and it's very large, it can explode. If it's slow moving in this very oblique angle, kind of hovering over the horizon, it can slam into the Earth, and that's exactly what happened here.
Tell us a little bit about the Chicxulub crater. When did that happen, and did it have any consequences for life on our planet? Bit of a leading question there.
So this is the granddaddy of asteroids. This hit about 65 million years ago.
Let's go back to the live images, please, while
Sure.
we're talking about other stuff. Thank you.
So well, I think I see it.
Yep, there it is.
There
So
it is.
carry on, Keith. You were telling
So
us about
Chicxulub, yeah,
Chicxulub.
this was what we call a species-ending asteroid. You know, when we get into a kilometer or a mile wide, we have serious problems. This was 6 to 9 miles wide by estimation.
Wow.
Left a crater that was 90 miles wide. And this is the asteroid that believed to contribute to the downfall of the dinosaurs. It
Yeah.
hit just off the Yucatan Peninsula in Mexico, and the crater and the shock waves extended out into the ocean. And, you know, we can think, how did this have an effect on the dinosaurs? You know, it's not like that's where all the dinosaurs lived and it created this damage. It created so much dust and debris that it kicked up into the atmosphere that it blocked out the sun for thousands of miles. And, you know, when you have the sun blocked out, plants can't feed themselves. They can't create chlorophyll. That's what the dinosaurs eat. And, you know, that's when you have the downfall of species. But this was a global impact, you know, 6 to 10 miles, which on that chart that we looked at, again, was among the smallest objects that we looked at when we look at the size
Exactly.
chart.
I think we need to thank that one, of course, because without it, we would not be here talking about it. Now, who knows? Dinosaurs may have evolved in intelligence and a technology so they could be monitoring near-Earth asteroids, but I don't know. I think the dice rolled in our favor there. Now, we've already talked about the 2013 Chelyabinsk event, but there have been other Earth impactors fairly recently too, haven't there?
Yeah, there was an asteroid in 2014 AA that crashed into the ocean, I think off the coast of Trinidad. That was observed. So again, this is another asteroid that we actually had a chance to observe, and I think they went to look for it. There was an asteroid in 2018 that crashed into the ocean, also somewhere, I think, around Hawaii, that they did find parts of it, pieces of it. And this is when, you know, things get a little bit concerning. We don't think that that asteroid came from the asteroid belt or from the Kuiper belt. We think this came from deep space. We think this is an interstellar object, and it's not the only one. 2017, we had Oumuamua visit us, and we think that was also interstellar. So not only do we have to worry about things in the main belt or in our solar system, now we're finding out that things are coming to us from deep space, and who knows how many of them are out there.
Wow. Now, Keith, before I let you go, we've talked about the potential and real threat these asteroids are to Earth, but many, including actually a whole bundle of people here who are attending the events here in Luxembourg this weekend, see them as rich resources to plunder. I'm looking forward actually to a lecture tomorrow by Dr. Catherine Hadler, who's the director of the, I need to get this right, the director of the Space Resources Innovation Center. Is all about space resource utilization. But what can you tell me about some of the opportunities and organizations and companies like this are looking at as far as plundering asteroids?
Yeah, asteroid mining has become a very hot topic. Obviously, we're not quite there yet, but asteroids are rich in resources that are very difficult to mine here on Earth. Things like gold and platinum and iridium. These have, you know, certain aspects in industry. They have industrial applications, and asteroids can't be one source for that. Probably not practical to send them back to Earth, but very important if they're used as sort of a stepping stone for a burgeoning space industry. And a lot of these
Mm.
asteroids also are comprised of water, at least water
Yeah.
composed in contained within rock. So very important for the manufacture of fuel, jet fuel,
Yeah.
rocket fuel.
An
So
incredibly important resource that they carry. But we now listen. Before we wind this segment up, as a teacher, I'm sure some of your students are interested in following careers in the space industries. What kind of opportunities exist for students in these areas?
well, everything from monitoring asteroids, working at one of these centers like the Minor Planet Center. There's a number of probably half a dozen different agencies that are monitoring asteroids. Anything involved in that. For mining, it's been said many times that the first person who figures out how to get to an asteroid and actually start a mining procedure will become the world's first trillionaire. So geologists, people that are able to work on all of the logistics of getting into asteroid mining, mining,
Yeah.
any type of, activity that would have to do with something like that, space travel.
Yeah, I was looking at the profiles actually of some of the keynote speakers here at Asteroid Day, and there's degrees in space engineering, there's degrees in aerospace engineering in the field of space flight dynamics, space resources utilization, is a chemical engineer, aeronautical engineering, and space techniques. And of course, development of edge AI capabilities for future Earth observation, environmental, and defense programs. So there really is a huge gamut of opportunity there for students. But I think with your students, Keith, Slooh really does help prepare them and put them on that path of career development, doesn't it?
No question. And the important thing I think is that it creates the desire, it creates the
Mm.
the sense of wonder and the wanting to learn more. And that's a huge step in taking us to, territory that we really don't know much about. A lot of these job positions don't even exist yet. But it is important to set the foundations, and Slooh certainly provides that.
Well, Keith, thank you very much for joining us this evening. It's been a pleasure talking to you as normal. Your wealth of knowledge is always greatly appreciated. So we'll see you later, I expect. Take care.
Paul.
Now, I would like to welcome back Slooh's Director of Curriculum, Dr. John Bovair, to walk us through the Quest animation tool for our special Colossal Asteroid Quest, and to talk about some of the other related Quest learning activities linked to tracking near-Earth asteroids. Welcome back, John. What do you make of these images? They're pretty cool, aren't they?
Oh, these images are really smashing. I really love watching them through the myriad of telescopes that are pointing at them right now. I've been snapping images from Canary 1, Canary 2 wide field, Canary 2 ultra wide field, Canary 3, and they all look awesome in their own different ways.
Excellent. Excellent. Oh, now I've got a little bit of news actually, because I didn't say this at the top of the show. But so we're looking at two telescopes, our Canary 1 half-meter telescope and our Canary 2 17-inch telescope. But we've also got a smaller telescope, but it has a far, far larger field of view. And that's our Canary 3 deep sky telescope. And although it's going to fall out of the field of view at around 10 past the hour in the Canary 1 and Canary 2 views, it's going to be visible in the Canary 3 wide field deep sky telescope a lot longer. So you can, if you've missed the beginning of the show and you haven't captured enough images yet, then you can carry on capturing those after the show. But John, I suspect you have captured a whole bundle of images, as you've said. Can you show us how students select the images they've captured in a quest?
Definitely. So the best way to get to the quest is by clicking quests on the navigation bar, go to all quests, and then you'll be able to search up Colossal Asteroid, and that'll bring you right to the Colossal Asteroid Flyby 2024. On step 2 of that quest is the spot for you to enter your data. And so if you've been capturing images from the beginning all the way to now and until after the party, there's actually 21 spots for you to put images in to make a really cool animation. But if you've only captured two is really the minimum number that you need.
Mm.
And so I'm going to show you what happens when we string together 3 images from the Canary 2 Wide Field Telescope. So when you click on Find Image, it's going to query all of the images of this asteroid. As you can
Wow,
see,
you
it's
have
like,
been busy, John. You have been really busy. Look at that. So all of these images that you've snapped from the live telescope are immediately available for you here.
immediately.
Great.
And what's really cool is when you click Find Image, it puts all of the images in chronological order. And
Great.
you can see the individual telescopes. Oops, you can see the individual telescopes that each of the images are from underneath uh, underneath the image. Now, I didn't really want to put this one in, so but if that
You can
happens,
change
all you
it.
need to do is
You
hit
can
Edit
change it.
Image,
Yeah.
and you can change it. So
Yeah.
what's really important in this data collection is that in this data collection module is that you put your images in chronological. So you'll have to scroll to the end of your page to see the earliest ones. But luckily, I know exactly the time of the images that I would like to use. So 2120 is the first one on Canary 2 Wide Field. And boom, so I've entered in that one image. All I need to do is do that a few more times. The other one is at 2124.
So you're selecting these. You're not selecting them sequentially, but you're selecting them a little bit further apart so that you're going to see more movement in your animation. Is that correct?
It's in part that, but also because I need to make sure that I'm choosing images from the same telescope
Yeah.
because the different telescopes that we have different size field of views. And so what this means is if you've been capturing images from multiple telescopes, you can actually create multiple animations, one for each telescope if you've been capturing them in multiple telescopes. So here we go. Here's the lesson. Okay, so I put in 3 images, and this should be a good teaser animation. Now I challenge
Okay.
students watching now to make a better, longer animation than the one that I'm
So
showing you
you've
now.
selected the images that you want. So
Mhm.
what do students need to do now to turn that into a time-lapse animation to show the asteroid moving against the background stars?
So underneath the data collection module, there's the create animation section. And if you've never used Slooh's animation tool, there's a really awesome primer that will teach you exactly what you need to do. But here, this is the Slooh's animation tool. And so frame 1 is the reference frame. This is where the stars are on the reference frame is where they're going to be for the rest of the animation. So when I click on frame 2, you'll actually see you can actually see the asteroid from frame 2 right here, and frame 1 is there. Now these images need to be lined up a little bit, and so there's this zoom function right here, where if I push the plus, it kind of it zooms in, and I can see the stars. Now with this right and left and up and down, I can move frame 1 with respect to frame 2 with respect to frame 1. And so you can see the stars are moving. So what you want to do is you want to get the stars right on top of each other. And what's really cool is you're right. You're spot on when all the stars get to be much
Yeah.
brighter than they actually are. So
Yeah.
so see here they're a bit dim, and now boom, that looks good. All right, so we can go to frame 3 and we need to do the same thing. Okay,
Looking
boom,
good. Looking
right?
good. Okay.
And we can do a test play on this. But actually, what we want to do is we want to zoom back out. We can do a test play, and there it is
There it is. It
moving.
is as simple as that. And now imagine that same thing, John, with how many images did you say students could use for this?
21
21.
images.
And the more images you use, the smoother the animation is because you see it slowly edge across the image. And you can change the speed and all sorts of things. And then once you've finished it, you can actually download it and share it with everybody, can't you?
That's right. I just hit the finish button. So this is a
Cool.
my first animation. And if I click on this button here, this is the download button. It'll save the GIF animation to your computer, and then you can share it anywhere and
And
everywhere.
it's given you a title of it. It's told you what the object is. It's got your name on it. I mean, I love this animation tool. So thank you, John, because I know you would have had to work furiously in the last 15 minutes while I was talking to Keith to make sure that live demo with images that you've only just captured went smoothly, and it did. So thank you very much. Good job. Now, let's move the topic on. Let's go back to hopefully some live images. We'll carry on looking at the live images, but let's talk a little about how students can use Slooh to track and monitor near-Earth asteroids. We've been on a 16-year campaign to highlight the threat and opportunities these space rocks have for humans. But do you know which asteroid jump-started Slooh's involvement with tracking asteroids?
I do. It was Asteroid 2008 TC3. I actually have an image of it right
I
here.
remember it well. There it
And
is.
Slooh is actually only one of only 3 organizations that was able to capture images of this 80-ton asteroid, only 13 feet in diameter, in the hours just before it impacted the skies over Sudan.
Yeah, I think it was about 3 hours before the impact.
It's amazing.
It is. It is.
And the event inspired Slooh to begin tracking all these potentially hazardous asteroids whenever they swung past the planet. And we've had Slooh members have submitted over 5,000 measurements to the Minor Planet Center, which houses the positional measurements for asteroids, comets, and other minor planets. So already Slooh is helping out figure out whether or not these asteroids are going to actually hit us or not.
And that they are very, very proud as well of their reputation at the Minor Planet Center for the accuracy of their submissions. Now, how can Slooh members track and monitor NEAs then?
The best way is by using advanced missions. So what's
a mission, John, first of all? We've got a mission, a live mission here on screen. What is a mission at Slooh?
A mission is a fixed time to capture a particular object with one of our telescopes. And so they're typically 5 to 10-minute reservations where, like I said, you choose exactly where you would like the telescope to look. And we have a Slooh 1000, which contains the 1,000 most beautiful, spectacular objects in the night sky. But we also have advanced missions that allow students to point the telescopes anywhere they want in the sky. All you need is right ascension and declination, and boom, you can start capturing potentially hazardous asteroids, near-Earth objects, comets, etc. And we have a lot of students that do that, and they submit measurements to the Minor Planet Center based on what they've seen from the advanced missions.
So why is this work important? Why are those measurements important?
Well, it's because it helps determine the orbits of the asteroids. It's vital for our safety here on Earth. Now, you really only need 3 measurements to define an orbit, but as with really anything else, the more measurements you have ends up helping you confine and constrain the model so that you better know what the orbits actually are. So this helps out.
Yeah, we see this on the JPL Horizons website, which is where you can go to look at, upcoming near-Earth asteroids and a whole stack of data about all of these objects. And they all have what's called a condition code, which I believe is 0 to 9. And it's basically, we don't really know where it is, all the way up to, yeah, we are dead cert of it. We know where this is, where it's going to be, over the next 100 years or so. But going back to how students can learn this, are there any Quest learning activities where students investigate asteroids or other moving objects in the solar system?
We do. The one that I'm thinking of the most is our Clyde Tombaugh quest, which Clyde Tombaugh was the scientist who discovered Pluto back in 1930. And in that quest, students recreate the discovery of the dwarf planet Pluto throughout the course of a few nights. Now, students end up piecing together their data to compare their images and see Pluto moving with respect to the background stars. And along the way in that quest, they learn about the story of Pluto's discovery and more facts about it, and a little bit about the New Horizons mission.
I absolutely love that quest. It's such a brilliant story of a farm boy who wants to become an astronomer, goes off to work at the Lowell Observatory. Some of the guest speakers here have quite a lot to do at the Lowell Observatory, so I'm looking forward to meeting them. But what you've just described there sounds like what students do in this Special Moments quest for the asteroid today.
That's right. I mean, both quests are using the same exact technique. It's just the major significant difference is UL21 is right next door, and Pluto is much further away, and also they're different in size. Pluto
Mm,
is about 1,000 times bigger than this asteroid, but because it's so far away from us, its orbital speed is not very fast. So your animations during that quest are going to look a little bit different than this. Instead of seeing a streak, you're just going to see a little dot. And so with only one image, you may mistake Pluto for just being another star. So those types, that quest, it's really important to, well, and this too, to capture images and actually piece them together. Use this our animation tool and the blink comparison technique to see it moving.
yeah. Just to remind viewers, if you've joined fairly late, or members, if you are watching, you've just joined us, make sure you snap some images of this, and you have to start the quest today. Otherwise, you won't be able to start it. But I was just going to say, John, let's have a look at that image again. So we've got the next mission starting. We can see the asteroid has moved on. As you say, the little streak of light there is the distance, the apparent distance that the asteroid has moved during the 50-second exposure of this. A little later on in the mission, we're going to see that second line appear over the top. And that's because in astronomical imaging, we normally combine images to increase the level of detail. So what actually happens is we combine the first image when the asteroid's here, and then we combine it with another image when the asteroid's already moved on. That's why we're seeing a dashed line on some of the live feeds. But are there any quests, John, that go into the dynamics of these objects in the solar system? Because I know a lot of educators, that's on the curriculum, covers a lot of core standards and stuff like that, doesn't it? Or involves a lot of core standards.
Yes, yeah, the one a great quest for that topic is our Kepler Planetary Motions quest.
Oh,
That
love that one.
particular Yeah, that one particularly covers how Johannes Kepler got the orbital data from Tycho, or well, the planetary positional data from Tycho Brahe in 1601, which led Kepler to determine the three laws of orbital motion that govern how planets, asteroids, even stars move in the night sky. And what's
Mm.
really cool is the quest goes through a lot of related topics too. It goes into Newton's gravitational force, kind of connects the idea of how Newton basically derived Kepler's laws from just using his gravitational force equation and F equals ma. And it goes into planetary configurations like opposition and conjunction. And it also talks little bit about the obliquities to the ecliptic, which is basically the rotation axis tilting of not only Earth, but the rest of the planets in the solar system. But I think
Uh,
my favorite thing about that particular quest is that it allows students to make personalized Kepler's laws
oh, yeah.
posters
So they
using
have a
their
poster. They have a poster for each law. And if people are new to Slooh today, the although the special quest today, the output that your students have from that is an animated GIF, time lapse animation of the asteroid crossing the field of view. The vast majority of quests culminate in an infographic poster that the students have created, custom created, doesn't it, John?
That's right, man. And not only is it custom based on the fact that the images that they put in are custom, and you can choose any object that any planet you want to use in any of these posters, but students can also edit the colors on the posters, the font, the literally everything on the poster is editable and customizable for the students. So it gives them a chance for their artistic expression to come through.
And all of the celestial images that they've captured are with Slooh's telescopes, and those are the things that go in to those posters. So it looks pretty good. Are there any quests related to asteroids in the pipeline?
There is.
Oh,
I can talk about a super fun quest that we have planned. It's called Wandering Stars. And that quest is going to follow Giuseppe Piazzi, who is the scientist that discovered the dwarf planet Ceres in 1801.
oh,
Keith mentioned Ceres in his segment.
mm,
Now, at that time, Ceres was actually announced as a new planet and later reclassified as an asteroid, the first asteroid, actually, the biggest asteroid, in fact. But according to our most recent definitions of asteroids, dwarf planets, and planets, Ceres is actually now a dwarf planet that resides in the asteroid belt between Mars and Jupiter. The quest is going to cover why Piazzi thought that there actually should be a planet at Ceres' location. And What's even more, and I'm so excited for this, is it's going to have a module that's powered by the Python programming language that will allow students to capture any asteroid they'd like using Slooh's advanced missions,
Very
particularly the
cool.
coordinate missions. So students will be able to select a date, an object, and then it's going to provide them with the mission times and the actual mission coordinates, the right ascension and declinations to schedule those missions. That kind of quest is going to be available for our high school and college students because of these advanced missions. Now, our curriculum team and our engineering team are currently developing those tools and technology to bring this quest to the platform. And like I said, I'm so excited for that one to happen. It's going to be a lot of
Wow.
fun.
So am I. That is going to
And
be so good. Now, John, these kinds of activities put students on a pathway to workforce development, don't they? It's something we and our industry partners are rather keen on encouraging.
that's right. They do. The science and skills that students learn at Slooh set them apart from their peers. They are
Mm,
learning and being inspired to pursue careers in space industries that's currently emerging
yeah,
worldwide.
yeah. So, what kind of careers can students pursue in the space industry?
There's plenty of opportunities in the space industries across many different fields, other than
Mm,
the obvious one of becoming an astronaut. On the science side, there's examples of careers for astrophysicists, planetary scientists, space weather scientists, planetary meteorologists. There's even space medicine physicians. Astronauts need to live in space
well,
after all.
yeah,
It's incredible how every science is basically needed for the space industry.
yeah,
But there's also an engineering side of it too. There's positions like aerospace engineers, satellite engineers, spacecraft system engineers, robotics engineers, propulsion engineers, and material scientists that are required to design and build the vehicles to take human satellites and probes into space. But what do all of these people that have these careers have in common? They have an inspiration by the universe and they're curious about the
yeah.
cosmos. Slooh start students on that path of inspiration and curiosity.
Oh, it does indeed. And we hear that so often from educators. Now, if there are educators out there who've got students or students watching tonight, what kind of subject should a student focus on throughout school to forge a career in the science side, say, of the space industry?
It's a really good question. Math is really the most crucial subject in developing skills for entering science.
Hmm,
Every branch of science uses math to describe the results of their experiments and to precisely describe the theories of the universe. I mean, obviously, science classes are important, but in your science classes, you will encounter math in them, especially physical sciences like physics and chemistry. Depending on what kind of science you're interested in, will determine if you need to take more specialized courses in mathematics. So, for example, or even just across the different scientific disciplines. So, for example, if you're interested in being a planetary scientist, then it's really good to take geology courses and earth science courses in high schools. But also, nowadays, science is done by relying on the computational power of supercomputers and
hmm,
laptops. So, computer science is another crucial subject to consider when the opportunity arises. In fact, when I first started doing astronomy research, and I was talking to a lot of my peers at the time, they all got asked the same question that I did when I first said, "Oh, I'm interested in astronomy." It was, "How good is your computer coding skills?" So, computer science is definitely important. Hard
for sure.
sciences like astrophysics, there's three subclasses. There's observational, theoretical, and computational. They're all a bit similar to each other and they do overlap a little bit, but they're all a little different. So, like observational astrophysicists, they focus on taking data from the telescopes. Theoretical astrophysicists concentrate on developing theories to explain the data coming from the telescope, and computational astrophysicists use computer science to test theories and data by creating simulations of different regions of the universe. So theoretical astrophysicists are more focused on math in their careers, whereas computational astrophysicists, of course, are more focused on computer science in their careers. So if you are pursuing or about to pursue a bachelor's degree, I would consider physics,
Hmm,
chemistry, geology, or computer science. Some positions in the space industry may require more advanced degrees than bachelor's degrees, like master's or doctoral degrees. But if you're interested in working in a national lab, for example, then a PhD is required. But as mentioned, there are positions out there that don't require that much of an advanced degree, and a master's degree is probably sufficient.
Oh, that's great advice, John. And so often is missing when we talk about workforce development. Just tell students the steps, the subjects that they need to focus on to take that next step to get in there. Interesting, you mentioned geology there, because a couple of the speakers here I know have got geology as part of their studies previously. It's the space utilization guys. But how about those preferring, we're winding up, so just keep an eye. We are still seeing the asteroid at the top left. It's just about to go off the edge of the screen, which is pretty cool. But how about those who prefer the engineering side of the space industry, John? What kind of steps should they follow?
So similar to science, math and computer science are both essential. Engineers, they need to have a good grasp of physical science and physical sciences and physics. Once getting to college, though, interested students should focus on an engineering degree. And there's many different types that are relevant to the space industry. So aerospace and aeronautical engineering is great for rocketry and the planes, drones, and helicopters that are now on all of the neighboring planets. But mechanical engineers and civil engineers are also essential for when we start developing establishments and living spaces on other bodies. Chemical engineers are important for helping develop the rocket fuel to get us there. Electrical engineers are crucial for developing the systems and
Mm.
rockets, satellites, probes, and everything else. And what's really great is typically a master's degree is sufficient for becoming an engineer.
That's brilliant. Brilliant advice, John. And look, perfect timing, because we can see the asteroid. It started off at the beginning of the show. It was down in the bottom left-hand side of this particular star field, and it's passing all the way across our image field, and it's just going to be exiting within the next 5 minutes. But don't forget, you can still capture images of it over the next 10, I think 20 minutes, something like that, in the Canary 3 Deep Sky telescope, because it's got such a large field of view. But it's looking pretty good there. It's looking pretty good. John, thank you so much for joining us and giving us all of that wonderful advice, and for explaining the quest as well. Hopefully we're going to see some animation shared of that, and we'll maybe share some of those in the last Slooh this week before the summer hiatus. So thank you, John, for joining us today.
Thank you for having me, Paul.
Well, that wraps it up for this special live star party to celebrate Asteroid Day weekend and to watch this colossal, potentially hazardous asteroid live in Slooh's mountaintop telescopes as it made its closest approach to Earth. It will, of course, return, as will many others, but those we know about, and also those that we don't know about. So why not get involved? Come and join us at Slooh to further your interest in astronomy and maybe forge a career in what is undoubtedly the most exciting and varied opportunity available to students today. So huge thanks to my two guests this evening, Dr. John Bovair and Keith Wozaleski. If you've enjoyed our coverage today, then make sure you join us again as we celebrate all manner of celestial events and phenomena, including eclipses, asteroids, supermoons, and solar storms. We've seen so much solar activity and solar flares and coronal mass ejections in the Slooh Solar Telescope over the last month or so. And of course, don't miss our upcoming star parties, where we're going to be celebrating our new Australian observatory coming online, giving us 24-hour coverage of the night sky. So that means wherever your students are going to school, they are going to be able to see Slooh's live telescopes. And we'll also be covering the forecast explosion of a star named the Blaze Star, which is forecast to go boom sometime in September when it goes nova. That is an absolutely unique opportunity, and we will have, John is developing at the moment a special moments quest to capture that as well. So we'll see it just as it normally is, and then we will see it rapidly brightened by a factor of maybe 100 when it goes nova. Quest will explain what a nova is as well. We are also working with JPL, the Jet Propulsion Laboratory, to provide them live coverage of Jupiter the day before their Europa Clipper mission sets off on its mission to explore one of the best candidates for life in our solar system beyond Earth, Jupiter's moon, Europa. If you haven't heard about the Europa Clipper mission, look it up on the internet because it is absolutely fascinating. And thank you very much, JPL, for inviting us to provide live feeds to your dignitaries the night before. We also have a Ring of Fire eclipse live from Chile later in the year. So there's lots to look forward to over the coming months. We hope to see you soon. But for tonight, that's all for now. Until next time, clear skies, everyone.